This is the first video in a chapter on stoichiometry of chemical reactions. In order to talk about chemical reactions, the first thing we need to know is the anatomy of a chemical reaction and how to balance one. So that's where we'll start. Looking back to where we were last time. Last time we learned some molecules will interact, but the interaction isn't that exciting, so we'll call it interacting lightly. Some molecules will interact lightly with different molecules when mixed. And that light interaction we called dissolution. Or sometimes they will not interact at all. We'll call that no reaction. So that's where we've been. And now we're going to move on to significant interactions, chemical changes that occur when compounds are mixed together. Now we will study what happens when molecules interact strongly, not an official term, with different molecules when mixed. And this strong interaction is a chemical reaction. So we've done dissolution. We have done when nothing happens. Now we're going to do when something happens, a chemical reaction. So to talk about chemical reactions, we need to talk about the anatomy of a chemical equation. So let's throw up a fairly simple one and we can identify the different important parts. Okay, so here's an example chemical reaction, and you're probably familiar with most of these terms, but it's best to go over them and make sure we're all on the same page. So a reaction has a left and a right portion. The left portion contains the reactants. These are the things that react at the beginning, and they form the things on the right, which are the products. So that will allow us to refer to the different compounds. We also have the bit in the middle, which is the reaction arrow. And this is going to be a slightly different reaction arrow than we've seen before. When we drew a resonance arrow, there was an arrowhead on both ends. This time our reaction arrow is just going to be forward facing with an arrowhead on the right. And sometimes, like in this case, some symbols are included with the reaction. So this particular symbol is a triangle, and that one represents that heat is needed for this reaction. You also might see a particular temperature or a particular pressure written here over this line that's needed for the reaction to occur. We also have physical states, and you can see those listed here in parentheses just to the right below each compound. So our physical states are going to be an S in parentheses for solid. They can be an L in parentheses, usually a cursive L, so it doesn't look like a 1 for a liquid. A G in parentheses for gas, or as we talked about in the last chapter, an AQ in parentheses for an aqueous compound, meaning that it is dissolved in water specifically. A little messy, so let's make sure we outline what goes together here. Okay, so we've got reactants, products, reaction arrow and symbols, physical states, and the last thing are these numbers, the big numbers that are listed in front of the compounds, and those are called stoichiometric coefficients. And these coefficients tell us how many molecules we have. So the oxygen has a 2 in front of it, meaning there are 2 oxygen molecules. And this methane does not have a number in front of it. If it's a 1, we leave it out, and that means there is just 1 methane molecule. And we're going to be talking about these coefficients a bit more later, but we'll introduce some of the significance now while we're here. The coefficients indicate the ratio of each type of molecule. That's why they're really important. That's what stoichiometry is all about. For example, there's a 2 in front of the oxygen and a 1 in front of the methane. So that means there's a ratio of 2 oxygen molecules for every 1 methane molecule. But it's a ratio. So we don't necessarily have to have just 2 or just 1. We just need the relative amounts to be 2 to 1. So we could say we had a ratio of 10 to 5. And that would still be equivalent because we would still have a ratio of 2 to 1. Or if we wanted to talk about lots and lots of molecules, we could even raise this to the level of moles. We could say we have 2 entire moles of oxygen molecules are needed for every 1 mole of methane. So we can use these numbers, the 1 and the 2 and the 1 and the 2, we can use those to produce ratios to tell us the relative amounts of each of the different types of compounds needed. But traditionally, when we balance the equation, we don't just write whatever number ratio we want. We like to simplify the ratio. So we like to simplify the coefficients to the smallest whole number combination. That way, when any type of scientist balances an equation and they look it up, everybody should have the same answer. So here's an example. If I react 6 hydrogen molecules with 3 molecular oxygens, I could make 6 liquid water molecules. But you can see that these are pretty large numbers, a 6 and a 3 and a 6, and I should be able to simplify those coefficients by dividing them by their greatest common factor. I can divide all 3 of these numbers by 3. So I could simplify this reaction by dividing by 3, giving me 6 divided by 3 is 2 molecular hydrogens. 3 divided by 3 is 1, so we don't need to list anything. 1 molecular oxygen. And 6 divided by 3 is 2 water molecules. So if you need to write a balanced equation and you see something that has a series of particularly large coefficients, you can simplify it by dividing by their greatest common factor. So those are all the parts you need to know of a chemical equation. And in the next video, we will talk about how to balance a chemical equation.